close your eyes and picture this, that blue in your eyes. It's not really there. The color you see is the exact same optical illusion that makes the sky look blue. 10,000 years ago, every single human on Earth had brown eyes. No blue-eyed pharaohs, no green-eyed priests, no gray-eyed Viking raiders. Then, sometime between 6 and 10,000 years ago, a newborn opened its eyes near the shores of the Black Sea, and the brown in its irises had been switched off by accident. In that moment, a human being saw blue for the very first time. Today, every blue-eyed person on the planet can trace their family tree back to that one baby. This isn't a legend, it's a genetic mistake. You're probably thinking, don't blue eyes come from blue pigment? After all, that's how we understand color. Dark skin comes from melanin, red hair comes from a reddish pigment, so blue eyes should mean blue pigment, right? But here's the stranger truth. The blue in your eyes and the blue of the sky are the same thing, and the sky isn't blue because the atmosphere is full of blue gas. Wait, what does that even mean? It means you've probably been misunderstanding your own eye color your entire life. But hold on, the really crazy part isn't the optical magic trick. It's why this mistake wasn't erased by evolution and instead exploded across an entire continent. Let's pull this story apart in 3 layers. First, where exactly the gene broke and drained the color from a continent's eyes. Second, why natural selection didn't fix it and may have even rewarded it. And third, what that blue actually is when you look in the mirror. Here's a clue. The most unique human features often come from losing something, not gaining anything. Let's fix a deep-rooted intuition first. There's only one key pigment behind different eye colors, melanin. Brown eyes have a high concentration of melanin in the iris. Blue eyes have a low concentration. Notice I said low, not zero, just less. Blue eyes still contain melanin, but it's mostly locked in the back layer of the iris, while the front layer is almost drained. Blue eyes weren't painted blue, they had the brown sucked out. It's like pouring out most of an espresso shot. That tiny leftover puddle no longer looks like coffee. So where did this drain command come from? It's buried in a stretch of DNA called HERC2. Strictly speaking, the mutation didn't hit a pigment, making gene itself. It hit a control switch that regulates pigment production. Imagine the melanin factory in your iris never shut down. The machinery's intact, the workers are there, the raw materials are piled up. But one day, somebody turned the dimmer switch on the wall down to the lowest setting. The factory still runs, but its output is locked at a trickle. That somebody is a single base pair mutation in HERC2. It didn't destroy any protein, didn't chop up any gene. It just tweaked a regulatory signal that happens to limit melanin production in the front layer of the iris. In 2008, a landmark study from the University of Copenhagen analyzed blue-eyed individuals from Denmark, Turkey, and Jordan around the HERC2 gene. Their DNA sequences were nearly identical. That uniformity points to a single origin. This mutation didn't happen multiple times. It happened once, in one person, a baby boy or girl, had a single base change from A to G during DNA replication. That baby survived, grew up, had children, and those descendants fanned out across the globe. When you spot a blue-eyed stranger in Stockholm, Sydney, or São Paulo, you're both sharing that baby's factory settings. But why this specific gene? Why the eyes and not the skin or hair? The OCA2 gene handles melanin production, and HERC2 acts like a remote master switch. It doesn't even sit next to OCA2, yet it controls it from a distance. The mutation landed in a regulatory region of HERC2, not the coding region of OCA2 itself. If OCA2 had been hit, the whole body's melanin system could have crashed, like in certain forms of albinism. This baby got incredibly lucky. The mutation surgically limited melanin just in the iris, everywhere else. Skin tanning, hair color worked perfectly. That dropped the survival cost of this mutation to nearly zero. Now the real question, even if the mutation didn't kill its carrier, basic evolutionary logic says a trait that reduces pigment should slowly get weeded out. Light irises are more sensitive to harsh sunlight, a clear disadvantage near the equator. So why did it dig in and thrive in Northern Europe? You might say, well, sunlight is weaker up north, so the disadvantage got neutralized. That's a fair thought. But hold on. Neutralizing a disadvantage is completely different from being actively selected. Was this drift, or was it selection? That's the deeper mystery we're stepping into next. And here's a question that gets creepier the more you think about it. Why did high frequencies of light eyes explode across Europe, but not in equally high latitude East Asia? If weak sunlight were the whole answer, the Mongolian steppe and Siberian winters would have plenty of it too. This hints that sunlight wasn't the only lever. Another invisible hand was nudging this gene's fate. Human desire, human beauty standards. This is where we step into part 2, survival or seduction. Which force was the real driver? Let's take the most popular hypothesis seriously, vitamin D. In the dim, low UV environment of Northern Europe, synthesizing vitamin D through the skin is already a struggle. If the iris blocks even more light, that's just making things worse. Lighter irises allow more ambient light to pass through the eye, not because the eyeball itself synthesizes vitamin D, but because researchers suspect light eyes and lighter skin tend to travel together as a package deal. A high-latitude light adaptation package. Pale skin is the main vitamin D factory. Lighter eyes may have been pulled along for the ride, a bonus feature bundled with the adaptation. But wait, if pure natural selection were driving this, we'd see a clean, linear gradient. The further north you go, the more blue eyes. Reality is much messier. Some Baltic coast regions have blue eye frequencies above 90%, while parts of Siberia at the same latitude sit below 20%. That's not a simple sunlight gradient. Something else got mixed in population history during the last glacial maximum. Northern Europe was basically uninhabitable. Humans contracted into a few warm refuges. One of those refuges sat near the Black Sea-Caspian region. When the ice sheets retreated, this small population re-expanded northward. And they happened to already be carrying that switch mutation. This introduces a crucial concept, the founder effect. You don't need natural selection to favor blue eyes. You just need the first people who walked into Scandinavia to have carried that blue eye gene at high frequency by pure chance. If they arrived first and later arrivals were few, blue eyes could become mainstream simply by showing up early. 10,000 years ago, a small group carrying the low melanin mutation stepped into an empty Scandinavia. They claimed the land, their population boomed, and the trait's frequency was amplified, not because it was better, but because it was first. In evolution, that's called neutral drift, a pure probability game. But even with the founder effect, if blue eyes were totally unattractive, hundreds of generations should have diluted it. No trait is that neutral. Here comes a force that might make you a bit uncomfortable: sexual selection. Imagine you live in a prehistoric community. Every single person has deep brown eyes. Then there's you, with pale gray, blue irises, like a winter sky. You're different, more than different. You're the only one. That uniqueness is an incredibly powerful signal on the mating market. Strange equals advantage. Novelty equals magnetism. Humans are a species deeply attracted to visual uniqueness, and our bias for novelty might have actively chased a mildly harmful trait for dozens of centuries. Sexual selection also has a terrifying self-amplifying power. Once a trait gets labeled attractive, carriers get more mating opportunities, produce more offspring, and those offspring keep carrying the trait, getting labeled, and getting chased within a few generations. A fringe mutation becomes a regional norm. By the time civilization arrives, this preference gets supercharged by writing, poetry, and art. Norse sagas describe heroes with frost-like gazes. Medieval troubadours endlessly celebrated noblewomen's pale eyes. That's not literary coincidence. That's culture continuously casting votes for a genetic variant. Blue eyes went from a random mutation to a deliberately preserved aesthetic asset in European culture. Now we can finally answer the East Asia puzzle. Why didn't equally high-latitude East Asia evolve high rates of light eyes? Because East Asia's demographic history is completely different. It never experienced the extreme Ice Age population contraction that Northern Europe did. Population sizes stayed larger, genetic diversity stayed higher, and the founder effect had almost no room to operate. Even more importantly, civilization emerged extremely early on the East Asian mainland. In those complex societies, aesthetic evolution marched in a totally different direction. Dark irises, like long black hair, were assigned an entirely different kind of beauty. Sexual selection there rewarded the preservation of dark eyes, not the pursuit of light ones. Blue eyes aren't destined to win everywhere. They require a very specific population history, a specific aesthetic environment, and a specific chain of accidents. So here's the evolutionary story we've assembled. A precise switch mutation, an isolated Ice Age refuge, a founder effect that grabbed the best seat, and then sexual selection plus cultural preference kept heating the pot until a minor variant boiled over into Europe's most iconic trait. But there's one more layer, and it has nothing to do with evolution. It belongs to physics. That blue you see in the mirror. It's not what you think. We need to talk about the optical conspiracy between the sky, the ocean, and your eyes. Let's do a simple thought experiment. If you could take a tiny slice of a blue iris, put it on a microscope slide, and shine transmitted light through it, you wouldn't see blue. You'd see a grayish, nearly translucent piece of tissue. The blue vanishes. That's because blue is not a pigment. Pigments are physical molecules. You can grind them up, and they still look the same color. Melanin molecules are blackish, brown no matter what. carotene molecules are orange. Your iris contains 0 blue molecules. That blue is a structural color, and nature is full of it. Peacock feathers, butterfly wings, the dazzling flash of a blue morpho butterfly. None of them contain blue pigment. Your eye's blue is the same trick of the light. This brings us to the Tyndall effect, discovered by John Tyndall in the 19th century, when light passes through a medium containing tiny suspended particles. Short wavelength blue light gets scattered much more easily, while long wavelength red light passes straight through. That's exactly why the sky is blue. Sunlight hits the atmosphere. Air molecules scatter the blue, and red goes right on through. What happens inside the iris? The front layer, or stroma, has had its melanin granules drastically reduced. In their place are masses of fine collagen fibers. Those are the suspended particles. When incoming light strikes them, shortwave blue light scatters out, while long-wave red light penetrates deeper and gets absorbed by the leftover melanin in the back layer. From the outside, all you see is the scattered blue. This explains an even weirder phenomenon. Blue eyes are not a stable color. The same pair of blue eyes looks deep gray. Blue on a cloudy day, vivid sky blue in direct sunlight, and even a little gray, green under warm indoor lamps. That's because the blue isn't painted on. It's being manufactured in real time, totally dependent on the spectrum of incoming light. Change the light, change the color. Green eyes work on a similar principle, just with a tiny extra bit of light brown pigment in the front layer. So the scattered blue mixes with residual yellow to make green. Gray eyes have an even denser scattering structure, scattering all wavelengths roughly equally to produce that silvery gray effect. These aren't different pigments. They're variations of the same scattering mechanism under different structural densities and different amounts of leftover melanin. This forces us to rethink a huge cognitive habit. We assume color is a property of objects. Apples are red, leaves are green, eyes are blue, but a physicist will tell you there's no such thing as a blue substance. There are only structures that scatter blue light and surfaces that absorb other wavelengths while reflecting blue. And evolution absolutely loves structural colors, because manufacturing a structure is way cheaper than inventing a brand new pigment molecule from scratch. You just tweak a developmental switch, adjust the spacing of some fibers, and boom, you've produced a never-before-seen visual color without ever building a new chemical synthesis pathway. That's why blue eyes could appear with a single switch mutation. They didn't invent a blue pigment, they just stripped away melanin and let the fibers build. And optical properties do the rest. So now we can retell the birth of blue eyes. 10,000 years ago, that newborn opened its eyes and its irises hadn't created anything new. They had simply lost a bit of melanin. And that subtraction, like pulling a few slats out of a tightly closed blind, let light stream through, scatter among the fibers, and refract blue out into the world for the first time. That baby didn't gain a color, it lost a layer of covering. Every blue, green, and gray eye that followed is essentially the same thing. Varying degrees of melanin reduction, exposing the scattering effect of the front iris fibers. Part of the diversity in human faces turns out to be not what the creator added, but what the creator forgot to block. At this point, we've unpacked all three layers of the blue eye, the genetic switch, the evolutionary forces, and the physics. Stacked together, they form a strange and enchanting story. A gene switch flipped into the wrong position. A post-ice age accidental migration, a round of sexual selection driven by human desire. And finally, physics presenting it as a blue that doesn't exist. This is a reminder. The most obvious features on the human body are often not carefully engineered solutions, but byproducts of a chain of accidents. And now we can nail down the core conclusion in one sentence. Blue eyes appeared and swept across Europe not because humans evolved a blue pigment, but because a single switch mutation in the HERC2 gene between 6 and 10,000 years ago reduced melanin in the front iris layer, allowing pre-existing collagen fibers to scatter blue light through the Tyndall effect. Then post-ice age population bottlenecks, the founder effect, and thousands of years of sexual selection teamed up to amplify this tiny genetic glitch into one of the most visible human traits on Earth. The blue in your eyes is not a substance, it's an event. The joint product of one genetic typo, one migration, and one massive wave of attraction. This reframes the very phrase, blue eyes. The blue you see in the mirror doesn't live in your genes or your iris cells. It's born the moment light leaves your eye. And more remarkably, without that 10,000-year-old mistake. All the poetry, the myths, the beauty standards, and the racial debates about blue eyes would simply not exist. The most fascinating human features are often not evolution's inevitabilities, but evolution's accidental side effects. We are not a designer product. We are error management. Let me leave you with one question. If blue eyes are the product of a genetic slip-up, how many other things we treat as normal are really just the echoes of some ancient accident? Tell me in the comments which body feature should we take apart next.